Okay, Assalamualaikum warahmatullahi wabarakatuh and good afternoon. Okay, so today we will continue with a new chapter, which is chapter 3. So chapter 3 is introduction to semiconductors. Okay, so as you all know that this subject, principles of electric and electronics, covers two parts, electric and electronics, and we have finished the electrical part, okay, up until the mesh analysis. So electrical parts covers the chapter 1 and also chapter 2 only. Okay, so after this, starting from today until the week 14, okay, so we will cover on the electronics part. Okay, so this chapter 3 is the introduction to semiconductors. Okay, so if you I hope that you still remember in your chapter 1 you have learned on conductors, insulators, and also semiconductors. So basically conductors is a material that very good to conduct current. Okay, and while insulator is a material that is very bad in conducting electricity or current. Okay, so these semiconductors falls in between the conductors and also the insulators. Okay, so it is not a very good conductors, but it is also not a very bad conductors. Okay, so these are the learning outcomes for chapter 3. We have 6 learning outcomes. Understand. Okay, so if you look at the words at the front here, LO1 is understand, understand, explain, 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 and describe. Okay, so based on these learning outcomes, you should expect that this chapter 3 is a fully theoretical base. Okay, so in your midterm test, so midterm test will cover until chapter 3. So do expect that the questions for chapter 3 is a theoretical base. Okay, no calculation at all. So if you refer in your slide for this chapter, there is no calculation at all. Okay. So we will finish all of this LO1 until LO6 today. Okay, so we can finish this whole chapter in one session. So first, let's look at the atomic structure. The atomic structure of a semiconductor. Okay, so over here it stated that every discrete solid state electronic device or IC. So IC is integrated circuit. Integrated circuit. Okay, begin with the highest quality semiconductor material. So basically the first thing when you want to design an integrated circuit, the most important thing is we need to use the highest quality semiconductor material. Okay, so this integrated circuit or the monolithic integrated circuit, or also referred to as IC, chip, or microchip. Okay, so all of these are the same. This is the what we call as IC. Okay, both of this. Okay, this is IC. Sometimes we call it as chip or microchip. Okay, so this integrated circuit is a set of electronic circuit on one small flat piece of a semiconductor material that is normally a silicon. So basically inside this integrated circuit, we have this. So inside this, we actually have this. We have a very small circuit, okay, on a small flat piece. This one, on a small flat piece of semiconductor material. And the semiconductor material that we usually use for the integrated circuit or IC is the silicon. Okay, so silicon is a type is an example of a semiconductor material. So I've already explained this one. So semiconductor, the conductivity is between good conductor and also insulator. So as we see here is the short form for semiconductors. Yeah? So we have conductor, we have insulator. So the semiconductor is in between the conductor and also the insulator. Okay. The conductivity is not as good as conductor, but not as bad as insulator. Okay, and for this semiconductor material, we can divide it into two classes. So the first one is what we call as the single crystal. Okay, the second one is the compound class. Okay, so the single crystal is a repetitive crystal structure. Okay, so we can actually determine whether the semiconductor is a single crystal or a compound directly based on its name actually. So over here, example of a single crystal, we have Ge. Ge is a germanium. Si, so Si is a silicon. Okay, and the second one is the compound. So the compound classes is constructed of two or more silicon semiconductor materials. Okay, so for example, we have the GAAS. So GAS over here, you can see that it is a combination of gallium and also arsenate. This one, it is a combination of cadmium and sulfate. This one is a combination of gallium and nitrate. And this one is a combination of three semiconductor materials, which are gallium, arsenate, and also phosphate. Okay, so the most frequently used in electronic devices is the germanium, silicon, and also the gallium arsenate. Okay. So this slide over here, just to show you the figure of a silicon and a germanium. So basically, silicon and germanium both are hard but tend to break. Okay, the material here, this one is very hard, but it is tend to break. Okay, hard and brittle. So for the silicon over here, you can see that it is a crystalline solid with a blue-gray metallic glow. Okay, so you can see that the color here is blue-gray metallic. However, for the germanium, the color is grayish white. Okay. Next, this is an example of a crystal structure. So over here, you can see the crystal structure differences between a single crystal and also a compound crystal structure. So this crystal structure is this is the crystal structure of a silicon. Okay, so this one is a crystal structure of a gallium nitrate. So gallium nitrate is a combination of gallium, the purple one is gallium, and the blue one is nitrate. Okay, so this figure is what we call as a crystal structure. Okay, and what is a crystal structure? So crystalline structure is the atoms that are bound together. Okay, so you can see that this is atoms and it is bound together. So that is what we call as a crystalline structure. Okay, so the fundamental components of atoms, this is standard. I think you guys already know that atoms consist of electrons, protons, and neutrons. So electron is negative charge, proton is positively charged, and neutron is neutral. Okay, no charge. Okay, so and next in the lattice structure, neutrons and protons form the nucleus, and the neutrons have zero charge. So if you look at here, I think you guys already seen this figure before in chapter 1 actually. You have the basically this is the nucleus. In the middle we have the nucleus, and the nucleus we have the neutrons and also protons. Okay, we have neutrons and also protons. Okay, so these neutrons and protons we call as nucleus. Okay, electrons is here. So electrons appear in a fixed orbits around the nucleus. Okay, proton and neutron is in the middle. Okay, so the combination of proton and neutron we call as the nucleus, and the electron is basically outside here. The atomic number or proton number is the number of protons found in the nucleus of an atom. Okay, so in chemical, biasa awak dah belajar chemical kan, biasa you have a symbol like this. So basically the number on top here is what we call as the mass number. The bottom one here is the atomic number. Okay, so what is mass number? Mass number is the number of protons plus neutrons. Number of protons plus neutrons in one atom, while the atomic number is the number of protons or electrons. Okay, so the atomic number, this one, we also call it as the proton number. So you should know that if we have equal number of protons and electrons, that means that the atom is neutrally charged. Okay, so if you have any question, you can just directly ask during the lecture. Next, this is electron configuration. Okay, so over here it's stated that Si is silicon. So silicon has 14 orbiting electrons. Okay, silicon has 14 orbiting electrons, and the number in this bracket over here, this is what we call as the electrons configuration. Okay, so this 2.8.4, this is the electrons configuration. Okay, so for example, we take this 2, 8, and 4. So what this number represent is that this 2 is the electrons, okay, in the first shell. Okay, number 8 is the electrons in second shell, and number 4 is the electrons in the third shell. Okay, so for the silicon, we only have 3 shells. Okay, 1, 2, 3. So usually for the outermost shell, okay, this one, we also call this as a valence shell. Okay, so this one we also call as the last one, we also call as the valence shell. Okay, so if I ask you how many valence electrons in the silicon, so the answer is 4. Okay, so this 4 is the valence electrons. Okay, the electrons in the valence shell, the electrons in the outermost shell. Okay, so basically maybe you have something like this. This is the silicon atom. Okay, the nucleus in the middle, and then you have 3 shell. the shell is actually the orbit. Okay, the shell is actually the orbit. So over here, for in the first shell, you have 2 electrons. So you have 1, you have 2. In the second shell, you have 8. So you have 1, 2, 3, 4, 5, 6, 7, 8. And the last shell, we have 4. 1, 2, 3, 4. Okay, so this is what it means by the first shell, second shell, and also the third shell. Okay, so this is the second one is germanium, Ge. Okay, so if you total 2 plus 8 plus 4, you will get 14. Okay, for the germanium, you have 32 electrons. So based on the electrons configuration, you can see that it has 4 shells. Okay, 1, 2, 3, 4. Okay, and the valence electrons is 4. For gallium, we have 31 electrons. Okay, also gallium has 4 shells, and the valence electrons is 3. While the arsenic, this is arsenic, has 33 electrons. We have 4 shells, and the valence electrons is 5. Okay, so that's why over here it stated that silicon and germanium has 4 valence electrons, 1 and 4. Gallium has 3, arsenic has 5. Okay, so over here you can see that atom with 4 valence electrons. Okay, so atom with 4 valence electrons, which means which is the silicon and germanium, we call as the tetravalent. Okay, for those with 3 valence electrons, we call as trivalent, and for 5 valence electrons, we call as a pentavalent. Okay, so arsenic is a pentavalent and gallium is a trivalent. Silicon and germanium is a tetravalent. Okay. So next, this is the structure, atomic structure that I already draw in the previous slide. So this is the atomic structure of the silicon. This is germanium, this is gallium, and this is arsenic. Okay, so remember silicon is 2.8.4. So you have 2 electrons in the first shell, 8 electrons in the second shell, and 4 electrons in the third shell or the valence shell. Okay, so the electrons in the valence shell we call as the valence electrons. Okay, so you can draw the atomic structure based on the electrons configuration. This one is also the same. This is the atomic structure. Same as the previous slide. This is the silicon, germanium, arsenic, and also gallium. So silicon has a total of 14 electrons. So if you add the electrons in each of the shell, you will get 14. Germanium, you have 32 electrons. Arsenic has Arsenic has a total of 33, and gallium has a total of 31 electrons. Okay. So next is covalent bonding. So what is covalent bonding? Okay, so over here, I stated that for a pure silicon or germanium, the 4 valence electrons of one atom form a bonding arrangement with 4 adjoining atoms. Okay, and this bonding of atoms is strengthened by the sharing of electrons. Okay, so what it means, you can refer to this figure. So this is the covalent bonding of the silicon atom, and this is the covalent bonding of germanium arsenic. Okay, gallium arsenic, sorry, gallium arsenic. So this the covalent bonding is actually the bonding of atoms. No, the arrangement, the bonding of one atom to another. Okay, so this is silicon atoms. Okay, so this bonding here is what we call as the covalent bonding. Okay, so what makes the covalent bonding strong is the sharing of electrons. Okay, you can see that for these atoms and these atoms, we have sharing electrons. Okay, so this is electrons in the valence shell of this silicon atom, and this is the valence electrons of this silicon atom. So this electrons, what we call as sharing of electrons. Okay, so this sharing of electrons is what makes the bonding strong. Okay, so if you remember, for silicon, you have 2.8.4. So the valence electrons is 4. So that's why you have 1, 2, 3, 4. So this is the ones that we show in the figure. This is the valence electrons. So the electrons in the second shell and also the first shell is not shown in this figure. Usually we draw the important one is the valence electrons. Okay, so for this covalent bonding of the gallium arsenic, you can see that we have, this is the atom for the arsenic, Kas. The Ga is the atoms for the gallium. Okay, so if you remember, for the electrons configuration for gallium, the electrons configuration is 2.8.18.3, while for arsenic, the electrons configuration is 2.8.18.5. So if you look at here, the gallium and the valence electrons is 3, arsenic, the valence electrons is 5. Okay, so that's why for the gallium over here, we have 1, 2, 3. Okay, 3 valence electrons. While for the arsenic, we have 5. 1, 2, 3, 4, 5. Okay, so the bonding between the gallium and also the arsenic is like this. Okay. Next, what is free electrons? Okay, so the following figure, the covalent bond, okay, will result in a stronger bond, okay, because we have the sharing of electrons. Okay, however, even though the covalent bond is strong, it is still possible for the valence electrons to absorb sufficient energy and to break from the covalent bond to move around freely. Okay, so basically, when the atoms are given heat, okay, so these valence electrons will have the energy, sufficient energy to break away from the covalent bond. Okay, so this free the electrons, valence electrons that break out from the covalent bond is what we call as the free electrons. Okay, so the free electrons is an electron that is not attached to an ion, atom or molecule and is free to move around when an external voltage is applied. Okay. So this one is the difference between a semiconductor and conductor. Okay, so this is the difference between the semiconductors and conductors. Okay, so the difference between semiconductor and conductor is in the application of heat. So if you look at here, for the conductor, if you increase the heat, the resistance will increase. But for a semiconductor, when you increase the heat, it will increase the level of conductivity. Okay, so basically, if you have a conductor, you increase the heat, basically the conductivity of the conductor will reduce. But for a semiconductor, if you increase the heat, okay, the conductivity of the semiconductor will increase. Okay, so that is the difference between a semiconductor and a conductor. So as the temperature rises, an increasing number of valence electrons able to absorb sufficient energy to break up from the covalent bond, and this contributes to the number of free carriers. Okay, so the increasing number of free carriers is the one that increase the level of conductivity of this semiconductor. Okay. Okay, so this one is just a repetition. I think this one you already know. The difference between conductor, insulator, and semiconductor. Conductor, I've already told you this many times. Conductor is a material that easily conducts electrical current. Example of a conductor, we have copper, silver, gold, and also aluminium. And for the insulator, it is a material that cannot conduct electrical current, while a semiconductor is a material that is between conductor and insulator. Okay, so it is neither a good conductor nor a good insulator. Okay, so the most common semiconductor is silicon, germanium, carbon, which contains of 4 valence electrons. Okay, so I have one question. Okay, for example, if I ask you to give an example of an equipment that consists of a conductor and insulator, can someone answer? Give me an example of an equipment. Okay, any equipment that consists of conductors and also insulator. Boleh? Sesiapa jawab? IC. IC. Okay. What about household equipment? Example of household equipment. Equipment that you usually use in your daily life. Any idea? Household equipment? Tak ada. Awak FK student tahu, lepas tu boleh jawab, FKM dia boleh jawab. Any household equipment that consists of insulator and conductor material. Peralatan rumah. Okay, tak ada, tak apa. But this question is very important. So do expect that for your midterm test or your final exam, the questions, especially for theoretical question, is not a straightforward questions. It's not a straightforward answer. Okay, you cannot get directly from the slide. Okay, because your test is an open book test. Okay, so the answer is not available in your slide for theoretical. So you need to think. Okay, So example is okay. I give you example of household equipment that consists of conductor and insulator. For example, is the kettle or water heater. Spoon. Okay, yeah, spoon. Okay, so one of your friends said spoon. Okay, so spoon also consists of conductor and insulator, because sometimes you have the spoon that has an insulator. Okay, like this. Okay, but if you have the spoon, the silver spoon without the insulator, okay, so this is this is mainly a conductor. Okay. Okay, so another example is kettle or water heater lah. Okay, so this is kettle. Okay, so usually the kettle, the body of the kettle is in silver, right? Silver in color. So this one usually for heating element, we use the kettle. The body of the kettle is a conductor. However, for safety purposes, the handle on top over here, usually we have a material, for example, rubber. Okay, so this is for protection. Okay, so actually there's a lot of household equipments that consists of conductors and insulator, and you also need to know, you also need to explain why for this equipment we need both conductors and also insulator. Okay. So next is energy levels. So figure 3. Okay, so in figure 3A, this is the energy level, discrete levels in isolated atomic structure. So if you remember your apa nama tu? You have the nucleus in the middle. You have the first shell, second shell. For example, you only have 3 shells. So the outermost shell here is the valence shell. Okay, so that is why I stated that the farther an electron is from the nucleus, the higher is the energy state. Okay, so this the nucleus is over here. So the farther the electrons, so meaning the electrons in the valence shell, the higher is the energy state. Okay, so basically that's why the energy, you can see that this is the energy, so the energy is increased. Okay, so the farther the electrons from the nucleus, the energy, the higher is the energy state. Okay, and in between the shells, okay, over here in between we have what we call as the energy gap. Okay, so this is we have the energy gap. Okay, so this is what it means based on the figure. Okay, so for this one, this slide is to show the difference, the energy level of an insulator, semiconductor, and also conductor. Okay, so over here is the insulator, this is semiconductor, this is conductor. So if you look at this figure, over here, this is the valence band or the valence shell. Okay, this one is the valence electrons. Okay, the electrons in the outermost shell. Okay, over here is the what we call as the conduction band. So if you look at for the insulator, the gap, okay, the gap between the valence band and also the conduction band is high. Okay, it's very big compared to the semiconductor. Okay, this one, the gap. For the semiconductor, you can see that the gap in between the valence band and the conduction band is smaller than the insulator. But for a conductor, the gap between the valence band and the conduction band is overlapping. Okay, conductor, the valence band and the conduction band is overlap. Okay, so what it means from this figure is that conduction band is to determine whether the material able to conduct electricity. Okay, so remember conductor, you know that conductor can conduct electricity, so that's why the band of the valence band and the conduction band is overlapping. It is already reached the conduction band. Okay, but for the valence band, for the semiconductor, you still have the gap over here. But if you give heat, okay, to the semiconductor, remember when you give heat to the semiconductor, the valence electrons in the valence shell will have the enough energy to break out from the covalent bond, okay, and it will become the free electrons. Okay, so that's why these free electrons can move to the conduction band. Okay, so it can become it can conduct electricity for a semiconductor. Okay, so that's why in the previous slide I told you that for a semiconductor, if you give heat, the conductivity will increase. Okay, for the insulator, you can see that the gap is very wide. So even though you give heat to the insulator, still the electrons, the valence electrons cannot reach the conduction band. That's why insulator cannot conduct electricity. Okay, so over here, for the semiconductor, okay, example of semiconductor, we have germanium, we have silicon, and also gallium arsenic. So if you look at here, germanium, the Eg, the energy here in between is 0.767 electron volt. So meaning for germanium, the electrons only need 0.67 electron volt of energy in order to go to the conduction band. Okay, for a silicon, it needs 1.1 electron volt, and for gallium arsenic, it needs 1.43 electron volt. Okay, so I hope that you can understand this figure. So this one I already explained based on the figure in the previous slide. So the germanium, I already told you germanium has the smallest gap. Okay, followed by gallium arsenic and gallium arsenic. And gallium arsenic has the largest gap, this one. Okay, so meaning that germanium only needs a small value of energy in order to reach the conduction band. Okay, but the gallium arsenic needs a slightly higher energy than germanium to go to the conduction band, to reach the conduction band. Okay, so this one, I think this is the same as in the previous slide. Okay, the energy levels of the insulator, semiconductor, and also conductor. Okay, so the energy gap, the unit is in electron volt, EV. So that's why in the previous slide, I told you that the germanium, the energy needs how much? 0 point something electron volt. Okay, the unit for the energy gap is electrons volt or EV. Okay, and this one, the important one in this slide is this one. So you should know that 1 electron volt is equals to 1.602 10 to the power of 19 joules. Okay, so this is for 1 electrons volt. Okay, so if you look at here, this one, the energy needed for a germanium to reach the conduction band is 0.67 and gallium arsenide is 1.43 electron volt. So can anyone answer which of this material has a highest sensitivity? Okay, between germanium, silicon, gallium arsenide, which one has the highest sensitivity? Can anyone answer?
Gallium arsenide kot.
Highest sensitivity. No, highest sensitivity is germanium. Okay, gallium arsenide has the lowest sensitivity. Why? Because germanium only needs a small value of energy. Okay, but for the gallium arsenide, it needs a higher value of energy in order to reach the conduction band. So basically, germanium has the highest sensitivity compared to the germanium, silicon, and also gallium arsenide. Okay. So, however, the sensitivity to changes in energy level can have a positive and negative effects. Okay, so sensitivity, it could be a good thing, it could be a bad thing. For example, for a germanium, okay, germanium has the highest sensitivity compared to the other two materials, okay, based on the previous slide. So for example, for applications that require high sensitivity, then you can use germanium. For example, photodetectors. Photodetectors is a light sensor. Photodetectors is a light sensor. So these light sensors are designed to be sensitive to light. Okay, sensor needs to be sensitive, needs to have a high sensitivity. Okay, so same as a security system. Okay, so security system are designed to be sensitive to heat. Okay, so basically it depends on the application whether you want whether the application needs a high sensitivity or a low sensitivity. So for these two examples, because it requires a high sensitivity, then you can use germanium. Okay, but for transistor networks, for example, where the stability is a priority instead of sensitivity, because sensitivity can be a harmful factor. So for application that requires stability instead of sensitivity, then you can use gallium arsenide. Okay. So next is semiconductor material classification. Okay, so this one is the same. You already know that semiconductor is in between a good conductor and also an insulator. Okay, so semi is how conductor is the material that can carry electricity. Okay, so the semiconductor material can be divided into two, which is the intrinsic. The second one is extrinsic. Intrinsic is a pure, for example, silicon and germanium, while extrinsic is where the semiconductor material is doped with impurities. Okay, so when you dope the semiconductor material with impurities, you can get either N-type semiconductor or a P-type semiconductor. Okay, so to get the N-type semiconductor, the semiconductor material must be doped with a pentavalent material with the 5 valence electrons. Okay, so example of a pentavalent, we have antimony, we have arsenic, we have phosphorus. Okay, and we also call this as a donor impurities. And in the N-type material, the majority carry is the electrons, while the minority one is the hole. For the P-type semiconductor, it must be doped with a trivalent. So trivalent is a material with 3 valence electrons. Okay, so we call this as acceptor impurities. And for the P-type, the majority of the carrier is the hole, while the minority is the electrons. Okay, so that's why we have N negative, P positive. Okay, so over here, already explained that if you want to have an N-type semiconductor and also the P-type semiconductor, you need to dope the semiconductor material with impurities. So what is doping? Okay, so over here stated that doping is the ability to produce a semiconductor of very high purity. Doping is an adding of one of the impurity into a semiconductor in order to relatively change the conductor from a poor conductor to a good conductor. Okay, so basically doping is you do doping in order to improve the conductivity of the semiconductor. Okay, so that is the short form what doping is, the function of doping. Okay, so this one, the doping process is adding impurities into pure semiconductor. Why we need doping? Because we want to produce N-type semiconductor and P-type semiconductor. Okay, so now let's look at the first N-type semiconductor. So to produce N-type semiconductor, you need to dope the semiconductor with the material with 5 valence electrons, or we call as donor impurities. Okay, so this will greatly increase the conductivity of the intrinsic semiconductor. Okay, so example of a pentavalent material with 5 valence electrons, we have antimony, arsenic, and also phosphorus. So over here, this example shows you the doping process of a silicon. This is silicon. Okay, silicon is an intrinsic semiconductor. You dope it with antimony. This is antimony. Okay, Sb is antimony. So you dope the silicon with the antimony, so you will get this structure. Okay, so remember, silicon has 4 valence electrons, Okay, you dope with a material with 5 valence electrons. 1, 2, 3, 4, 5. Okay, so the doping, the result of the doping, you will get this. So over here you have, this is the antimony, this is the silicon. Okay, so this is the valence electrons. So the silicon has 4 valence electrons. Okay, so you have 1, 2, 3, and 4. For antimony, you have 5. 1, 2, 3, 4, 5. Okay, so you have an extra electrons here. Okay, so that's why, because we have an extra electrons, we call it as a donor impurity, where it contributes to a free electrons. Okay, so this is the free electrons. Okay, so because the pentavalent atoms give up an electrons, that's why we call as a donor atom. Okay, penderma. Okay, so this is the N-type semiconductor. Now let's look at the P-type semiconductor. So P-type semiconductor, you need to dope this intrinsic semiconductor with a trivalent, okay, material with 3 valence electrons, or we call as acceptor impurities. So example of a trivalent, we have boron, indium, and also gallium. Okay, so in this example, we show you the doping process of a silicon with a boron. Okay, so silicon has 4 valence electrons. Boron is a trivalent, it has 3 valence electrons. So if you dope the silicon with the boron, you will get this structure. Okay, so silicon, you have 4 valence, 1, 2, 3, 4. Boron, you only have 1, 2, 1, 2, and 3. Okay, 1, 2, and 3. And you have a hole. Okay, because you don't have enough electrons. Okay, so the acceptor impurity creates a hole. So because the trivalent atom accepts up an electron, it is called an acceptor atom. Okay, so this one, for the P-type, you can see you have a extra hole over here. This one, for N-type, you have extra electrons. Okay. Next, this is the difference between the P-type semiconductor and the N-type semiconductor. So if you look at here, just look at the importance. So for the N-type semiconductor, this is the important words. You need to dope it with the pentavalent. Okay, dope it with the pentavalent. For a P-type, you need to dope it with a trivalent. Okay, so and the second one over here, the impurity atoms are added to provide, it will provide extra electrons, and we call as donor atoms. But for the P-type, it creates the vacancies of electrons, okay, or holes, okay, and we call it as the acceptors. And the last one, for the N-type semiconductor, electrons are the majority, but for the P-type, the holes are the majority charge. Okay. Okay, so you already learned about the N-type and also the P-type semiconductor. Now let's look at the semiconductor diode. So basically, you will learn in detail about diode in chapter 4. Okay, so chapter 4 is a whole chapter about diode. Okay, but before that, this is just a to show you the relation between the n-type p-type with the development of a diode. Okay, so if you look at here, for both n-type and p-type, the number of protons and the number of electrons are equal. Okay, so when you have equal number of proton and electrons, then you can say that this material is neutrally charged. Okay, so a diode is basically created when n-type and p-type are placed in close contact. Okay, now we are talking about diode, semiconductor diode. So diode is created when the n-type is placed in close contact with the p-type semiconductor. Okay, so when it is close contact, so in between the n region and the p region, we have what we call as the p-n junction. Okay, so over here, recall that the p region has many holes. Okay, remember the majority in the p region, p type is the holes, while the majority in the n region is electrons. Okay, free electrons. So now let's look at what is depletion region. So remember, in between the PN junction, we have the PN, in between the PN, P and also N region, we have the PN junction. So at the instant of PN junction formation, free electrons, okay, the free electrons near the junction in the N region will diffuse, will spread across to the P region. Okay, and this will create a layer of positive charges. Okay, so the combining of electrons and holes depletes the holes in the P region and the electrons in the N region near the junction. Okay, and because of that, we have a depletion region over here, caused by the combining of the electrons and holes depletes the holes in the P region and the electrons in the N region. Okay, so this is the I think you can read this by yourself. The depletion region process in detail. Okay, but the ones in the previous slide already explained in general, but this one is in more detail. So I hope that you can read this by yourself. This one is also the same. It's just that to show you the barrier potential. Okay, so what is barrier potential? Remember, we have P region, we have N region. So basically, the potential difference of the electric field across the depletion region is the amount of voltage required to move the electrons. So basically, for the electrons in the N region to move to the P region, there is a required voltage, okay, where the voltage for the silicons is 0.7, the voltage for germanium is 0.3 volt. Okay, and over here we call as the barrier potential. So barrier potential is the potential difference expressed in volt. So basically, what it means that for the free electrons in the N region to move to the P region, it needs to satisfy this voltage, okay, required voltage. Okay, so silicons need 0.3, germanium needs 0.3 volt. And okay, so this is already towards the end of chapter 3. So this is the semiconductor material application. Okay, example of a doped semiconductor is diode. I think maybe some of you already know what is diode, right? Sebab ada yang daripada diploma, you should know what is diode. Okay. So diode is a equipment that only allows one direction of current. Okay, so this is the symbol of a diode. Remember, if you still remember. Okay, you have positive side, negative. So the current can only flows one direction only. Okay, it can only flows in one direction. It cannot flows like this. Okay, so the diode actually consists of a P junction and also N junction. P-type semiconductor and also N-type semiconductor. Okay. So the combination of the P and N doped semiconductor materials, okay, so basically the hole will diffuse to the N region, while the electrons in the N region will diffuse to the positive region. Okay, so basically we will learn in detail about this diode in chapter 4. Okay, so I haven't uploaded the chapter 4 yet. Okay, so chapter 4 will cover solely about diode. Okay, diode structure and also the diode application. Okay, so any question for chapter 3? Intro to semiconductor. Okay, so you can see that this is all theory. Okay, semua theory. You don't need to remember, but you need to understand. Okay, because you don't have the face-to-face exam. Okay, you have online exam and it's open book, so you should understand, not remembering. You don't need to remember the definition and so on. Okay, no question will be asked about the definition or something like that. Okay, so any question before we end our lecture for today? Any question about your midterm
Doktor,
test tutorial?
saya nak tanya pasal midterm test.
Ya.
So midterm test memang chapter 2 dan the whole chapter 3 ni lah.
Ya.
Okay.
Actually, chapter 1 pun ada relation dengan chapter 3 juga kan. Kalau ingatlah conductor, insulator, material, that one is also in chapter 1. So, but mainly is chapter 2 and chapter 3. Okay. So, chapter 3, theory. Like I said to you before, it is theory, but the majority of the questions is from chapter 2. Okay, so do expect the calculation is from chapter 2. Okay, so that's why I asked you to do the tutorial to really understand, able to solve the tutorial questions, because the questions for the calculation part is solely from chapter 2. Okay, so your midterm test is 1 hour 30 minutes. You will have maybe 20 minutes extra time for you to upload. Okay, so 1 hour 30 minutes is solely for you to answer your question. Okay, so because you're a first year student, so basically your midterm test is similar to your quiz. Okay, so you need to write your answer in a piece of paper and then make sure that you you convert it to PDF and then you upload. Okay, but please please follow the time that we already set. Okay, I don't want macam hari tu masa quiz ada yang hantar dekat email kan, so saya tak nak macam tu. I want all of you to submit your test through ULearn. Okay, because we already gave you enough time. Okay, impurities for p-type. Siapa? Tadi siapa yang tanya? Okay, so your midterm test is on